All right. How's everybody doing today? Wunderbar. Good to see you all. Hope you all are equal. It means wonderful in German. Although this is not a German class, this is a math class, so we're going to focus on math today. All right, so we just start. You have a timer? I mean, I don't want to go over or anything. This is difficult. We good? All right, so today, everyone, we're going to talk about probability and expected value. We've got an interesting little topic here. Probably see a lot of this today with all of the rest of our teachers. So I'm going to give you a task today. It's called Gina's counters. Cool? So the idea here is Gina's got a bag of counters, right? She has, oh, I'm blocking the projector. That's not good. She has a bag containing counters that are red, green, yellow, and white. All right? And we're going to look at probabilities based on a few given sets of rules that Gina has for her bag of counters, okay? So, here are the rules. And Hazel, since you're sitting up front, will you read the first rule of the bag?
The probability of a red counter from the bag is 1/2.
Everybody get that? So probability of picking a red bag from the counter is 1/2. Ansley, rule number 2.
The probability of picking a green counter is half the probability of picking a red counter.
Everybody got it? So probability of picking a green one is half that of picking a red one. And last but not least, Jordan, can you see it in the back?
Yeah, blue, yellow, and white counters have an equal probability of being picked.
Make sense? Everybody kind of got a good idea? So what we're going to do right here is I'm going to hand you out this little worksheet with all the stuff. I'm going to ask that you don't try to work ahead. We're all going to kind of stay together on this. But we're going to try to determine the probability to start off with. We're going to use this information to complete the table. It's going to decide what the probability of picking each counter is in the bag. Now the rules are still up there on the board. So feel free to talk about it with your neighbor. So use these rules and we'll have a conversation about it in just a second. See if everybody's on the same page about figuring out the probability of picking each counter out of this bag. I want to put my hands behind me, but that clip is right there. Put it on the side. Any questions, any ideas? Everybody should have filled out the first box, right? And by the first box, somebody tell me what the probability of picking the red counter is.
The first clue is 1/2.
Clay, wonderful work, buddy. Good job. All right, so the probability of picking a red counter is 1/2, right? So we know from the second rule, what's the probability of picking a green counter?
1/4.
And why is that, Ellie?
This is 1/2 of 1/2. Because red is 1/2.
So explain to me what you're doing there mathematically. Are you dividing 1/2 by 1/2? Multiplying 1/2 by 1/2? Did anybody else do it differently?
I divided 1/2 by 2.
Oh, awesome. Everybody kind of get the idea how that's kind of very similar? Good work. All right, so now we got to figure out blue, yellow, and white. Anybody have any ideas? Hazel.
So you add up the red and green probabilities, and that gives you 3/4. And then it says that blue, yellow, and white counters have an equal probability of being picked. So you have to do 3/4. You have to separate 3/4, or like divide 3/4 by 3 to get what blue, yellow, and white would be.
Say a little more about that. You said divide 3/4 by 3.
Yes.
Wait, how'd you get 3/4?
Yeah, I got that from the red and green. So I added the probabilities of the red and green. So I just converted 1/2 to 2/4, and then 2/4 plus 1/4 is 3/4. Oh, 1/4. 1/4
Yeah.
divided by 3.
Okay. So everybody see where Hazel got slightly confused there? So basically you have red's probability is 1/2, right? You add that to the 1/4 that you decided that the green was a probability, that gives us 3/4 of our probabilities there, right? So the blue, yellow, and white can only make up what's left of probability in there. Remember, all of our probabilities in a single instance have to add up to 1, right? So what she did is she took 1/4 and understands that 1/4 has to be divided evenly, like that last rule says, between blue, yellow, and white. So what was our probabilities of the last ones? 1/12? Cool. Awesome. Good work. Anybody have any questions about that? Everybody kind of good? Cool. So let's talk about how many counters are in the bag then. You now have a probability model of what the probability of drawing each different color counter is in the bag. So can you come up with how many counters are in the bag of each one? Take a second, talk to your neighbor.
Yeah.
Can it be 12? Yeah. Yeah. Right. Holy, right.
You're right.
6 times as many red, blue, yellow,
Not just one answer.
twice as many red.
Could there be more than one answer?
That's a good point you've got there, Mr. Jordan. We'll see. If you want to challenge and be creative, then by all means, let it happen. Okay, in the interest of moving this along, somebody give me an idea of how many counters they have of each color in the bag. 12. There are 12 total counters?
There could be.
There could be. Explain.
Because, well, basically what I did is made all the denominators the same thing, and I made them all 12. Because I noticed that there's 3 categories that had denominator 12.
Okay, so then you have how many of each counter?
I have 6 red, 3 green, 1 blue, 1 yellow, 1 white.
So you have 6, she has 6 out of 12 for the red, and that gives you a probability of drawing red of 1/2. 3 green sticks to the 1/4, and then 1/12 of each of the other colors gives her 12. Did anybody else have a different answer? So everybody found the least common denominator of 12? Wow, that worked out great. It's going to be easy. Cool. Just so you know, it is possible to have more than 12. Anybody give me any other possible values now that we've talked about the least common denominator? Sure. 24. Why?
So you could double the numerator in each of these fractions, so you'll have 12 red, 6 green, 2 blue, 2 yellow, and 2 white, and that'll still equal the correct fractions.
Anybody want to challenge that?
You said just double the numerator.
But when she said it, she also did double the denominator too. Yeah, she said double the numerator, 24, but she also said 12 reds. Cool, that makes sense. So it could be 24, 36, 48, as long as the total number in the bag is divisible by 12, right? Cool. Good work. All right, so here, let's get to the meat of this thing. So Gina is working at her local fair. She's trying to raise funds for her charity, right? She plans to charge 10 cents for people to draw a counter out of the bag, okay? She's going to pay 20 cents to anyone who picks a blue counter, 50 cents to anyone who picks a yellow counter, and $1 to anyone who picks a white counter. So that means that anyone that picks a red or a green counter will lose their money. Cool? Does everybody have any questions about this? You got it on the back of your page if you flip it over. We already did that? Cool. So, first problem with this. Can somebody explain to me why Gina's going to lose money in this game? Take a second, talk to your neighbors. Think, pair, share.
Charges 10
There's
cents.
3 different ways for her to lose the money that she got.
You get 20 cents.
Oh, that's $1. I thought this.
Oh, it's because everyone is going to win.
That might be a good thing if you understand what expected value is. Yes. It would be great if you'd bring that up when we talk, Ansley.
Well, so that's 1/4 that you'll lose money just no matter what.
Yeah. It was like,
And then if she finishes,
We'll struggle.
loses money, sometimes she loses a lot.
Because it's gonna be.
A lot of math going on over here.
Losing is always more than
Uh-oh. Ansley's absolutely right. Okay, again, interest in moving along since we're on a time frame today. Somebody give me a conjecture about why they think Gina's going to lose money in this game and explain.
There's a negative,
Say that again, Ansley.
the negative expected value.
What's an expected value?
That is a great question. Ansley, do you think you can explain expected value to Clay?
It's how much, well, I'll
Okay.
answer. It's how much that, sorry, it's what you're expected to get after a long, many trials.
Okay, that's one way you can think about it. So what they're talking about here is expected value. What we're looking at is what can Gina expect to get based on this probability model and her payouts and take-ins. Does anybody have an idea quickly why they can explain how she's going to lose the game with actual like mathematical value as opposed to just expected, like using the definition of expected value? No? All right, so we decided that there were 12 counters in the bag, right? And what pays out?
Blue, yellows, and whites.
Okay, so how many of each one of those is in the bag?
112.
All right, so if someone draws a blue, how much does she pay out?
20 cents.
Okay. And if someone draws a yellow, how much does she pay out? And if someone draws a white, what does she pay out? And those three numbers added together,
170.
$1.70, right? So if she plays 12 times, you can expect probability-wise that each of those is going to be drawn one time in 12 plays, right? How much money does Gina bring in 12 plays? So if Gina, as Jessica was saying, over a length of time, and obviously we can stretch this out to playing it 100 times, a million times, we can figure out what it takes to play one time, what her expected value is. But ideally, we've put 12 counters in the bag, so we can look at this in a manner of if we played this 12 times, she's only going to bring in $1.20, but she can expect, based on probability, to pay out $1.70. Right? So, with that in mind, what can Gina do to change the game? What can she charge to make sure that she makes money? Obviously, she's not charging enough money, right? How did you come to that?
Oh, wait, no, sorry. That would be if it was 10 games.
Okay. Do you think she would break even if she charged 17 cents?
I think she would get more. She would get more.
Charge.
Why about 15, Clay?
Because $1.70, about half of that would be around 80, but we got around 120. So just add around half of that charging fee, which
Okay.
is 5 cents, to get to 180.
Anybody else have any ideas about what Clay's saying? Rachel? Ellie? Anybody back here? No?
10 cents got me $1.20,
Then 15 cents going to get you,
an extra 50%, which would be $1.80.
okay, and $1.80 is more than $1.70? Cool. So she needs to charge at least 15 cents. She charges more than that, then her expected value should be higher. Okay, so then now between the three of you, and this is last little part here, awesome, good work guys. Try to determine a way Gina can change the game and still charge 10 cents and make money. Ooh. I hear a lot of stuff. Jordan, tell us what you're thinking there, buddy.
I said she could not give out $1 for the white counter.
Okay, so what's that going to do?
If she gives less, then her expected value is going to go up. And it also, just kind of compared to the other prices, seems a little strange because going from 20 cents to 50 cents and then jumping up to $1 in
Okay.
the context of having only paid 10 cents is kind of strange.
So it seems a little outlandish, but mathematically, can you explain why not charging that $1? Like what she needs to do about that $1 to make sure that she makes money?
She could drop it to either one of the other prize amounts, 20 cents or 50 cents, like the blue or the yellow counter.
Okay. And that would kind of ensure that the amount of money that she paid out is less than the amount of money that she can expect to take in, right? Expected value. Yay, good job, guys. Time up. That's it?